Hello everyone, welcome to the Edexcel IAL October 2020 S1 paper solution. So let's start with question number 1. The discrete random variable x takes the values -1, 2, 3, 4 and 7 only. So we have a discrete random variable x and it can take on these values, and here is the probability distribution. Now usually we see a probability distribution written as a table, but it can also be written as a function like this one. So we'll put it in tabular format just to make things easier for us, but let's read what this function is for now. So given that the probability of x being equal to some value is equal to 8 minus that value, small x, divided by k, for all the values of x. Find the value of the expected value of x. Okay, so we need to find the expected value of x. Now, one thing that we see is k is unknown, so we obviously cannot find the expected value if there is this unknown here. So we need to solve for that k, and to do that, we use an implicit piece of information just from the fact that we're dealing with probability, is that the sum of all the probabilities needs to be 1. Well, first, as I've said, we've put this into tabular format. So let's look at this. When x is equal to -1, then the probability is 8, 8 minus 1. So 8 plus 1, 9 divided by k. So for -1, the probability is 9 by k. For 2, it's 8 minus 2 by k. So 6 by k. And so on and so forth. So we have filled this table with the corresponding probabilities. Now, as I've said, the sum of all these probabilities has to be equal to 1. So if we add all of them up, this has to be equal to 1. And if we solve this, we get a value of k, which is 25. Now, since k is known, we can actually find the expected value of x. The expected value, the formula for that is, well, what you do is, this is how I like to remember it. You multiply each x with the corresponding probability in each column, and then you just add all of those up. So if you do that, that's what we did here. So -1 into 9 by k, well, the k is 25. Now all of these probabilities are known. This is 9 by 25, this is 6 by 25, and so on and so forth. So -1 times 9 by 25 plus 2 times 6 by 25 plus 3 times 5 by 25 plus 4 times 4 by 25 and plus 7 times 1 by 25. So we all add all of them up, and now we get our final answer of 41 by 25. Now that's the expected value of x. Question number 2. In a school canteen, students can choose from a main course of meat, which is M, fish, F, or vegetarian, which is V. They can then choose a drink of either water, W, or juice, which is denoted by J. Now, the partially completed tree diagram, where P and Q are probabilities, shows the probabilities of these choices for a randomly selected student. So we have a tree diagram here which is incomplete. Now, part A tells us to complete the tree diagram, giving your answers in terms of P and Q where appropriate. All right, so first thing we can see is that we have a blank here. Now, the rule for tree diagram is branches on the same level. And what I mean by that is branches that come out from the same point. The sum of the probabilities for those has to be equal to 1. So these 3 branches, they come from the same point, and so their sum has to be equal to 1. So this one is 1 minus the rest of them, 0.4 and 0.35. So we get a value of 0.25 here. Same thing here. We have only 2 branches. One of them is unknown. So the unknown one is 1 minus the other one that we know. So 1 minus P. Same thing here. If this is Q, the complement here is 1 minus Q. If this is 0.4, the complement here is 1 minus 0.4 or 0.6. So we have completed the tree diagram. We have filled up all the gaps. Part B. Find an expression in terms of P and Q for the probability that a randomly selected student chooses water to drink. So let's first bring up that tree diagram again for reference. Now what we need to find is very simple. We need to find the probability of W. probability that a student chooses water to drink. Now, there are several paths that lead to water. So we could go through meat and then to water, so from M and then to W, or we could go through fish. Student could choose fish and then also water, so from F to W, or we could go through this route here, vegetarian and then water, so from V and then W. So and the way we work with a tree diagram when we see these types of paths going through branches and reaching the endpoint is we just multiply through all the probabilities in a single path. So suppose this probability, the probability of choosing meat and then water, is just going to be the product of these two probabilities on the way. So the probability is 0.4 multiplied by P for this one. Same thing with the rest. So we go through F and then W. We see that these probabilities are on the way, so we just multiply them through. And also this one, it's the same. So we see this one, this probability, and this probability. That's what we have on the way here. So we just multiply them. So 0.25 multiplied by 0.4, and we get an answer. This is as expected from the question. This is in terms of P and Q. It's not a numerical answer. So it's 0.4 times P plus 0.35 times Q plus 0.1. That's as much as we can simplify this. The events choosing a vegetarian main course, and they give a name for this already. This is V. And choosing water to drink, and they also give a name for this. This is W. Are independent. So this is pretty interesting that V and W, they're independent. Find a linear equation in terms of P and Q. Now, independence of two events implies a certain number of equivalent conditions. You could say that the probability of the intersection of the two events, so V intersection W, is just going to be the product of the probabilities of V and W. So we could use this condition, and there's also the fact that the probability of one event happening is independent of whether the other happens or not. So you could say something like this: the probability of V given W, well, it doesn't matter whether W happens or not. So the probability of V is going to be the same. So the probability of V given W is still the same as the probability of V. Now, or you could do this with, interchanging those positions too. W given V is the probability of W. Now, what statement are we going to use? Which of these formula are we going to use? Well, we found the probability of W before. We found the expression for that. So it would be beneficial if we use something that relates to that. So let's bring up the tree diagram again. And since W and V are independent, as I've said, the probability of W has to be the same as the probability of W given V. So this is the third possibility that I talked about. All of these are equivalent to each other. They're equivalent formulations. Why am I using this? As I've said, we already found this expression. So if we could find a numerical value for it or simplify it in some way, that could help us to find an equation in terms of P and Q. Now, it actually turns out that it's pretty simple, because the probability of W given V, well, if we look at the tree diagram here, given V, so we have already crossed this path. Now we are here. And so from here, what's the probability of W happening? Well, it's very clearly 0.4. There's no confusion there. Given that we have already crossed this path and we are now here, the probability of W happening is 0.4, just this much. Now, this is going to be equal to 0.4 from the tree diagram, as we have deduced. So we will equate our expression that we have already found to 0.4, and this gives us an equation in P and Q. So 0.4P plus 0.35Q is equal to 0.3. So this, let's call it our equation 1, and this is because we'll find another equation and solve them simultaneously. Now, one thing that might this slightly irritates some of you is why am I not simplifying this even more? So I could take out the decimals like multiplied by 10 or 100 and simplify it in some ways. However, that's not really necessary or even optimal here because we are dealing with probabilities. The other equation that we're going to find is also going to have decimals, and it's going to be easier to solve them if this is just left as it is. So just this much is fine. A student who has chosen juice to drink is selected at random. The probability that they chose fish for their main course is 7 by 30. So it's already given that the student chose juice. All right. So we are given J. And so the probability that they chose fish, given that they chose juice, is 7 by 30. So this is what they're trying to tell us. The probability of F given J is equal to 7 by 30. Now, let's bring back our tree diagram before working on this. So this is what they've told us. The probability of F given J is equal to 7 by 30. And this is going to lead us to the solution if you use the conditional probability formula. Before trying to do that, we need to find a few things. First thing, we need the probability of J. Well, choosing juice and choosing water are complementary events. There are two types of drinks, juice and water in this situation. And choosing the one is the complement of choosing the other one. So the probability of J is just going to be 1 minus the probability of W. Well, we already know what the probability of W is. We saw that that is equal to 0.4. So this is going to be equal to 0.6. Now, back to our conditional probability. So the probability of F given J is equal to 7 by 30. The formula for conditional probability is if you have the probability of A given B, this is going to be the probability of both happening at the same time. So the probability of A intersection B divided by the probability of the given event happening. So the probability of B here. So if we apply the formula in the same pattern here. So it's the probability of both F and J happening at the same time, F intersection J, divided by the probability of the given event or J happening. So this is going to be equal to 7 over 30. Now, the probability of F and J happening, well, that's just we need to do what we have done so far. Just go through this path. So just multiply through these two probabilities. So the probability of F intersection J is 0.35 multiplied by 1 minus Q. So that's that right there in the numerator. Divided by, we already found the probability of J, that's equal to 0.6. And so this is going to be equal to 7 by 30. We have an algebraic equation with only one unknown. So we can easily solve for Q, and it turns out to be 0.6. Now, since we have found Q, P is pretty easy to find. We already found an equation that has P and Q. There, if we make P the subject, P is going to be equal to 0.3 minus 0.35 Q divided by 0.4. We just made P the subject in the equation we found earlier. And if you plug in the value of Q here, we get a value of P of 0.225. So we have found both P and Q. The canteen manager claims that students who choose water to drink are most likely to choose a fish main course. So part E tells us to state, showing you're working clearly, whether or not the manager's claim is correct. Now, first I'll discuss what the strategy is here, and then we can proceed to solving this. Well, there are three possible routes we could take for the main course if we have already chosen water. So student who has already chosen water, so it's always given W. So we could choose fish, or we could choose meat, or we could choose vegetarian. So V given W. And since these all are based on already having chosen water, they come from the same point, you could say, if you draw that type of a tree diagram. The sum of them has to be equal to 1. So given, I think it makes sense, given that we have already chosen water, we could possibly choose just one of these three, and the sum of these has to be equal to 1 because we've already chosen water. The total probability in this situation has to be equal to 1. So these are all the possible scenarios, and their sum has to be equal to 1. And what the manager claims is this probability that choosing fish, given that the student has chosen water, this is the largest among these three. So how can we show that? First, we might think that if we find all these three and compare them with each other, this one should come out the largest. That's how we'd solve it. But an even easier way is, since we know that their sum is equal to 1, if we just show that this is greater than 0.5, then the others definitely have to be less than 0.5. So this definitely has to be the largest one. So all that we need to show is the probability of f given w is greater than 0.5. So first, let's bring up the tree diagram as reference again. So this is the tree diagram. Now, the probability of f given w, that's just going to be equal to, according to our conditional probability formula, it's the probability of f intersection w divided by the probability of w. Now, the probability of f intersection w, as we have seen before and we have done before, it's just going through this path. So it's the probability of 0.35 multiplied by q. So q is 0.6. We have already found that. And the probability of w, as we've seen before, that's equal to 0.4. So this turns out to be 0.525. And that is clearly greater than 0.5 as we expected and we're aiming for. So given that this is greater than 0.5, as we have already talked about, this implies that this is the largest. This is larger than the probability of m given w and also larger than the probability of v given w. So this supports the manager's claim. The manager's claim is correct. Question number 3. The distance achieved in a long jump competition by students at a school is normally distributed with mean 3.8 meters. So 3.8 is the mean mu and standard deviation 0.9 meters. That's sigma. Students who achieve a distance greater than 4.3 meters receive a medal. So receiving a medal is equivalent or means that the jump distance was greater than 4.3 meters. All right. So part A tells us to find the proportion of students who receive medals. So first, let's name our variable. So let j be the distance in meters of a jump. So j is normally distributed with the mean of 3.8 meters and a standard deviation of 0.9, so a variance of 0.9 squared. This is just writing this in notation. The main thing starts here. We need to solve this. What's the probability of getting a medal? And that's the same as the probability of j being greater than 4.3. That's the same. So this is going to be equal to the probability of z. Well, why are we not directly finding this? Why do we need to convert this to anything? Well, we cannot actually just find the probability for any given distribution, normal distribution. We can only find the probability if it's a standard normal distribution, which has a mean of 0 and a standard deviation of 1. So to convert our value to the standard normal distribution, we are going to use this formula. So the equivalent z value for our j value is z is equal to the value here, the value in this distribution is 4.3 minus our mean, which is 3.8 meters. This is 3.8 meters divided by our standard deviation, which is 0.9. So j being greater than 4.3 is equivalent to z being greater than this converted value right here, this converted z value that we have right here. So this is going to be equal to, if you simplify this, the probability of z being greater than 0.56. Now again, there's a problem. From the large table, we cannot actually find the probability of z being greater than something. It can only be the probability of z being less than something, some positive value actually. But to convert that, it's pretty simple. We know that the probability of being greater than something and being less than something, specifically less than or equal to something, these two are complements of each other. So this is equal to 1 minus this. And it doesn't really matter whether we write less than or less than or equal to here, because normal distributions, those are continuous distributions. So less than and less than or equal to, or greater than and greater than or equal to, those are equivalent. So this is going to be equal to 1 minus this value is from the large table. So 0.7123 turns out to be this probability value of z being less than 0.56. And we get the final answer of 0.2877. The school wishes to give a certificate of achievement or a medal. Now, this is where I'd like to insert a small comment here. They unnecessarily made the question a bit more confusing by writing or a medal. This medal doesn't actually mean the same one as we saw before. This is just a certificate of achievement, not the same as the medal that we saw before, which is for J is greater than 4.3. That's different. Later in the question, when they refer to getting a medal, that's actually referring to the one that we already saw, where they definitely get a medal if they get J is greater than 4.3. Here it's uncertain whether it's a certificate of achievement or a medal. Anyways, I felt that writing this was pretty unnecessary because it just convolutes the question. All right. So the school wishes to give a certificate of achievement or a medal to the 80% of students who achieve a distance of at least d meters. So we need to find the value of d. That's what part B asks of us. So by definition, the probability of j being greater than d or greater than or equal to, that means the same thing. This is going to be equal to 80% or 0.8. That's what the question literally tells us. So if we convert this to our standard normal distribution, we get the probability of z being greater than d minus 3.8 divided by 0.9. So d minus the mean divided by the standard deviation is going to be equal to 0.8. Now, you might think that we can proceed in the same way as before, just convert this to less than 1 minus z less than this value, then use our large table. However, this probability value and values like this, which are like 0.1 or 0.15 or 0.8 or 0.7, I like to call these ones neat probability values, although that's not a mathematically rigorous term. And the reason why I call them like this is, for these we should actually use the small table. In fact, marks will be deducted if we do not use the small table and use the easier route of using the large table. So we need to use the small table here. However, the small table only applies for the probability of z being greater than something is equal to a probability value which is less than 0.5. So we need to bring it to that format. So to do that, what we are going to do is use a few conversions. The first one might seem a bit counterintuitive. However, we will get to our destination. Now, the probability of z being greater than something is the same as the probability of z being less than the negative of that something. And this is pretty easy to see if we draw a diagram here. Suppose, say, this is our standard normal distribution. This is the mean 0. Suppose, say, this is negative a and this is a. So the probability of z being greater than a, that's this area. The probability of z being less than negative a, that's this area. And we can see very clearly that by symmetry, a normal distribution is always symmetric about its mean. So by symmetry, these two areas or probabilities are equal. So the probability of z being greater than this value is going to be the same as the probability of z being less than the negative of this value. And this is going to be equal to, again, 0.8. Now, this step might seem counterintuitive because we have actually strayed further from our format that we wanted here. We wanted a probability value of less than 0.5. We don't actually have that. And we need greater than here. We had that, but we actually changed that to less than. So it seems like we went further from what we desired. However, using one more step, we're actually going to make a beeline for this format. And that is that the probability of z being less than this value It's the same as 1 minus the probability of z being greater than this value. These two are complements. These two are complementary events. And this is the same value as this one. Actually, I just multiplied the minus through the numerator. Now, this is going to be equal to 0.8. And if we simplify this, if we make this probability the subject, we get the probability of z being greater than this value is equal to 1 minus 0.8 or 0.2. Now we have achieved this format that we wanted. Our probability value, its need value, that's less than 0.5, and we have z greater than. So now we can actually use our small table. So using our small table, the corresponding z value to 0.2 is 0.8416. Now this has to be the same as this. So from here we can get the value of d, which is 3.04256, or to three significant figures, it's 3.04. Of those who received medals, the 1/3 who jumped the furthest will receive gold medals. Now, as I've said before, this medal refers to what we saw in part A, J being greater than 4.3. All right, so this basically means that the probability of getting a gold medal, given that the student has already achieved a medal, is going to be equal to 1 by 3. Now, part C tells us to find the shortest distance, g meters, that must be achieved to receive a gold medal. So, if we translate this mathematically, we get that the probability of getting a gold medal means that j is greater than g. So, or greater than or equal to, that would mean the same thing. So this is equivalent to getting gold medal, and getting a medal is the same as j being greater than 4.3. Now this is going to be equal to 1/3. So using our conditional probability formula that we saw before, the probability of a given b is equal to the probability of both happening at the same time, a intersection b, divided by the probability of the given event, the probability of b. So this is going to be equal to the probability of both happening at the same time. So you're supposed to have j greater than g intersection j greater than 4.3. Now, why have I just written j greater than g here? And that is because j being greater than g actually implies that j has to be greater than 4.3. Note the question here. Of those who received medals, a smaller proportion of them will receive gold medals who jump the furthest. So the gold medal winners, the distance for winning a gold medal is even greater than the minimum distance for winning a medal. So G by definition has to be greater than 4.3. So this condition is actually redundant in the numerator. We can just write J greater than G here. So that's the numerator, and the denominator is the probability of the given event, j greater than 4.3. Now this has to be equal to 1 by 3. Now the probability of j being greater than g, if we make that the subject, this is equal to 1/3 of, this is just the answer of part A. So we plug that in here and we get 0.0959. Now if we convert to our standard normal distribution, we get the probability of z being greater than g minus 3.8 divided by 0.9. This is equal to 0.0959. We cannot actually use the small table here. This is not a neat probability value. So what we are going to do is convert this to z being less than something. That's what we need to use the large table. So this is going to be equal to 1 minus the probability of z being less than the same value, and it's going to be equal to 0.0959. The right hand side is unchanged. So the probability of z being less than this value is going to be equal to 0.9041. Now this exact value is actually not in the large table, so we need to choose the closest one. So the probability value, the closest one is 0.9049. That's the closest to 0.9041, and the z value for that is 1.31. So g minus 3.8 divided by 0.9 is approximately equal to 1.31, and that means that g is approximately equal to 4.979, or to three significant figures, that's 4.98. A journalist from the local newspaper interviews a randomly selected group of 3 medal winners. So they've already, all of them have won medals. We know that. Part D. Find the exact probability that there is at least one gold medal winner in the group. Now, in these situations where they ask, find the probability of at least one thing happening or there at least being one thing in the group, it's usually easier to find the probability of none happening and then subtracting that from one, because none happening and at least one happening, those two are complements, as we can understand from the phrasing. So that is going to be our strategy here. The probability of getting a gold medal, as we saw before, the probability of getting a gold medal, I'll write G here, given that the student already got a medal, this is equal to 1 by 3, as we saw before. So the probability of not getting a gold medal, given that the student has achieved a medal, is going to be 1 minus that. It's 1 minus 1 by 3, and that is going to be 2 by 3. Now, the probability that all these 3 medal winners did not receive a gold medal, that's the none probability that I was talking about. So this is just going to be 2/3 multiplied 3 times. So all 3 of them did not receive gold medals, and the probability of that, given that they received a medal, that's 2 by 3. So 2 by 3 cubed, and this is going to be equal to 8 by 27. Now we just need to subtract that from 1. So this is the complementary event. At least one receives a gold medal. So the probability of that happening is going to be equal to 1 minus this probability. And that is going to be equal to 19 over 27. Question number 4. A group of students took some tests. A teacher is analyzing the average mark for each student. Each student obtained a different average mark. For these average marks, the lower quartile is 24. So this is the lower quartile, or Q1. I'll label this Q1. The median is 30. So this is the median, or Q2. And the interquartile range, IQR, is 10. We are not given the upper quartile, but we should be able to find it easily. We have Q1 and the IQR. Now, the 3 lowest average marks are 8, 10, and 15.5. So these are the 3 lowest marks, and the 3 highest average marks are 45, 52.5, and 56. So these are the upper and lower extremes, you could say. The teacher defines an outlier to be a value that is either more than 1.5 times the IQR below the lower quartile. So 1.5 into IQR below Q1, or more than 1.5 times the IQR above the upper quartile. So these are the bounds for the lower and upper quartile. So if it goes beyond these bounds, it's going to be an outlier. All right, so part A tells us to determine any outliers in these data. So obviously, first we need to determine these bounds, and then according to that, we need to declare which of these extremes are outliers. Now, before finding these bounds, we actually need the upper quartile Q3 for this one, but we do not have that. However, we know that the IQR is going to be Q3 minus Q1. And we already have the IQR and the value of Q1. From here, we can solve for Q3. That turns out to be 34. Now, the upper bound for the outliers, as has been stated here, it's 1.5 into IQR above the upper quartile, or this added to the upper quartile Q3. So if we evaluate this, we get a value of 49. Let's see which of the marks are actually above 49. So not 45. This is actually the highest mark that's not an outlier, as we'll see. So and that's because it's 49, and the ones that are beyond that is 52.5 and 56. So I'd just like you to keep in mind that 45, this mark right here, is the highest mark that's not an outlier. And so the outliers on this end are 52.5 and 56. These are greater than 49, and so these are outliers. The same thing on the lower end. The lower bound for the outliers is going to be 1.5 times the IQR below. So this is subtracted from Q1. So if we evaluate this expression, we get a value of 9. So which ones are below 9? That's only 8. 10 is above 9. So only 8 is below 9. So only 8 is an outlier on this end. 10 is the lowest value that's not an outlier. Again, I'd like you to just keep that at the back of your mind. And so the outliers are 8, 52.5, and 56. Part B. On the grid below, draw a box plot for these data, indicating clearly any outliers. So first, let's draw the quartiles. So the box part, which has these 3 quartiles as vertical lines. So Q1 is at 24, as we previously saw. Q2 is at 30, and Q3 is at 34. Next, let's fill in the outliers. These we're going to indicate as asterisks, and these are the 3 outliers at 8, at 52.5, and at 56. Then the 2 whiskers. Now, as I've said before, 10 is the lowest value that is not an outlier. So this is going to be the left whisker. And 45 is the highest value that is not an outlier. So this is going to be the right whisker. And this is our complete box plot. Part C. Use the quartiles to describe the skewness of these data. Give a reason for your answer. So in these skewness questions where we need to use the quartiles, it's basically a comparison between these 2 quantities or differences, Q3 minus Q2 and Q2 minus Q1. Q2 minus Q1. So if the former is greater than the latter, then it's going to be a positive skew. If it's equal, we have a case of symmetry, and if it's less, then we have negative skew. So let's see what happens here. We need to first find these two and then compare them. Now, Q3 minus Q2, Q3 is 34, Q2 is 30. So 34 minus 30, that's 4. Q2 minus Q1, that's 30, that's Q2, minus Q1 is 24. So 30 minus 24, that's 6. We clearly see that Q3 minus Q2, which is 4, that's less than 6. That's less than Q2 minus Q1. So according to what we discussed, the data is negatively skewed. 2 more students also took the tests. Their average marks, which were both less than 45. Now, I'm just marking this for the moment. We'll need it not in this question, a bit later, are added to the data and the box plot redrawn. The median and the upper quartile are the same. So the median, it was 30, it's still 30. The upper quartile, it was 34, it's still 34. And the lower quartile, but the lower quartile is now 26. It was 24 before, now it's 26. So in part D, they're telling us to redraw the box plot on the grid below. Now, this question might seem very simple where only the lower quartile changes. So we might think, okay, so if I just change Q1 from 24 to 26, we should be done. However, if you remember, our lower and upper bounds for identifying outliers, those depend on the lower and upper quartile and the interquartile range. Here, since Q1 is changing, the IQR is definitely changing, and those bounds change. So our outliers might be different. Not necessarily so, but they might now be different. We need to verify. So first, let's see what's the IQR. The interquartile range is now, it's Q3 minus Q1. Q3 is still 34. Q1 is now 26. So 34 minus 26, that's 8. So our upper bound, we need to recalculate. These are our upper and lower bounds for outliers. So our upper bound is Q3 plus 1.5 times the IQR. So this turns out to be 46. Remember that our 3 highest marks were 45, 52.5, and 56. So out of those 52.5 and 56, those 2 are greater than 46. So these are the 2 outliers on the right end. It's still the same as before. Now let's check the left end. The lower bound is now Q1 minus 1.5 times the interquartile range. If we plug in our new values, we get a value of 14. Now, this means that since 8, 10, and 15.5 were our lowest values, 8 and 10 are now less than this lower bound. These are the outliers on this end now. See, before it was only 8. Now 10 is also an outlier. So the outliers are now 8, 10, 52.5, and 56. Now we have all the information that we need to draw this diagram. First, let's draw in the quartiles like before. So the only difference here is that Q1 is now 26. These two are still the same. Now let's fill in the outliers. So there are 4 now at 8, 10, 52.5, and 56. Last but not least, we'll fill in the whiskers. So the left whisker is now 15.5. Why? Because before 10 was the lowest mark that was not an outlier. Now 10 is an outlier, and the mark that's the third lowest, it's 15.5 as they told us, and that is actually greater than 14. So this is not an outlier. So 15.5 is the lowest value that is not an outlier now. So that is the left whisker. And 45 is still the highest value that is not an outlier. So it's still the right whisker, the same as what it was before. Part E. Give ranges of values within which each of these students' average marks must lie. Now, when they say each of these students, they mean those 2 new students' marks which were added. So we need to find the range in which each of these marks must lie. So let's analyze the changes and see how that affects where these marks must lie. So first thing, Q1 has increased from 24 to 26. This implies that, okay, so it would be better if I just draw a small diagram here. So suppose the Q1 is at some position like this. Now, one thing, they actually haven't told us the sample size or n. However, since it's increasing by 2, we can say that at most the position of Q1, which is n by 4, at most that's going to increase by 1. It might not, but at most the position might increase by 1. Whether or not that happens, the fact that Q1 has increased from 24 to 26, it was nudged in this direction, the right direction, suggests that both those marks must be to the right of 24. And in fact, they actually have to be greater than or equal to 26. Why? Because if there was a 25 among them, as I've said, the position can only at most increase by 1. So if there was 25, if one of these 2 marks was 25, Q1 would actually be 25 right now, but it's 26. So we know that maybe none of them are 26, maybe they're even greater, but at the very least they need to be greater than or equal to 26. All right, so that's the information from there. Now Q2 is unchanged, and so that means that the marks are on either side, or they might even be equal to the median, which is Q2. Now this is the same as pretty same as the discussion here. Why have I said that Q1 increasing means that the mark lies to the right? Well, if the marks lie to the left, then Q1 would have decreased. And if the marks lied on either side of Q1 or on Q1, Q1 would have most likely, and it would have actually stayed the same. So none of those are what actually happens with Q1. However, here that's what happens. It's unchanged, Q2. That's why the marks, they can lie on either side of the median, or they might even equal the median. And the same thing, the same type of information we get from Q3. Since Q3 is unchanged, the marks are on either side of it, or they might even equal this upper quartile, which is 34. And last but not least, we are given one more piece of information from before, is that both marks must be less than 45. Now we have 4 different conditions here. The marks must be greater than or equal to 26. They lie on either side of the median, or they might even equal the median. They lie on either side of the upper quartile, or they might even equal the upper quartile, 34, and they must be less than 45. The only way to satisfy all of these is, let me draw a simple diagram here. So suppose say this is Q1, suppose say this is Q2, suppose say this is Q3, and suppose say this is our right whisker. This is our right whisker, which is 45. Now, as I've said, the marks must be greater than 26, both of them. So one of them, we could think it's somewhere here above 26 or equal to 26. From here up to, as we can see, it can lie on either side of the median. So if I decide that one of those lies on the left, suppose say one of those lies on the left, might even equal the median. So from here to here inclusive, that is where one of the marks lies. Now that's, suppose say we call that M1. All right, so the other mark, as you can see, one of the other marks must be on either side or on the upper quartile. So on either side or on the upper quartile. Now, one of them is already on the left of the upper quartile. As you can see here, M1, we are deciding that it's on the left of the upper quartile. Now, the other one must be to the right. According to this condition, as we can see, it must be to the right, or even on. It might even be on this upper quartile. So from here, inclusive, up to here, and it's not inclusive here because they said it must be less. Both marks are less than 45. So from here to here, and this is less than 45. So the two ranges for the marks are, one of the marks is between 26 and 30 inclusive. So greater than or equal to 26 and less than or equal to 30. The other mark is greater than or equal to the upper quartile, 34, and strictly less than 45. So these are the two ranges in which the marks must lie.
Follow us on social media: Facebook, YouTube, Twitter, Snapchat, Instagram, and LinkedIn. So, don't be late. Enroll to your desired courses and let Bizuz be the guide to your dream grades.